and refreeze this water and make ice. But in what you find is in doing that, the surrounding is warmer than it was in the initial state. Okay? So you could make this back into ice, but the surrounding you'll find that it won't go back to its original state. If you could do that, then this would have been a reversible process. Okay, so all processes in nature are irreversible. Okay. Here is a close approximation. So let's say this is an air hockey puck. Okay, let's say it's floating here, and I can move it here, move it like that, move it like that, and I can take it back. And that's almost reversible. Why is that reversible? When would it be reversible? If it were totally frictionless, then it would be reversible. Okay. All right. So anyway, so why is it that we define these things? I mean, in nature, all processes are irreversible. We idealize reversible processes because we'll use that to get upper limits on things. Okay, so these are useful theoretical devices. Just like we always solve problems in physics 1 without friction. Have you ever encountered a frictionless system? No. But okay, so that's what this serves here. Okay. All natural processes are known to be irreversible. Okay. So I gave you a couple of examples. All right, now let's go back to our mechanics. How much work do you do when you lift an object? When you lift an object through H, work done is force times, this is the force you applied. You had to apply a force equal to the weight. And if you lifted it through a distance H, it's that, which is mgh. Okay. So when you lift an object against the force of gravity, you've done work, and that's how much work you've done. Yep. Now, so let's say here's a gas. This is a piston. And Sophia, you're early. All right, so we heat the gas. What will happen? This piston is movable. And the gas will expand and it'll lift up. So a gas is capable of doing work. Okay? And now we'll find out how much work it does. So if this is open, right now the pressure in the gas is atmospheric pressure, a little more than atmospheric pressure, depending on the weight. And so the work done by this expanding gas, it turns out is equal to, if the pressure is constant, pressure times increase in volume. Okay. And if the pressure is changing, then the infinitesimal amount of work done is the pressure at that point times the change in volume. Yeah. So we want to know this because in a lot of our systems, we'll be using gases to do our work. Can you think of an example where you're using gas to do work? In the car engine. Okay, it's the air fuel mixture that's doing the work. Okay. All right, so here, the infinitesimal amount of work done when this piston expands is the force times the small distance the piston moved. Force is pressure of the gas times the area. Area times that is the volume change of the gas. Okay. So when the volume of the gas changed by that much, that's how much work it did. Okay? And P is the pressure of the gas. All right, so let's say the gas volume changes a finite amount and the pressure is changing along. But you guys are calculus experts. Okay? How do you calculate the total work done? the total work done is just the sum of the infinitesimal amount of work. Okay? It's P dV. Well, P, of course, is a function of V. That's how you calculate the work done. Okay? And in calculus, you've learned that if P is a function of V, you go from the initial point to the final point. The work done is the area under the curve. Okay? All right, so here are various PV diagrams. Okay, so here's pressure versus volume. Here's the initial state, here's the final state of the gas. How many different ways can you go from the initial state to the final state? An infinite number of ways. You can see I've listed infinity minus 4. Okay. So you can go from this initial state to the final state in a number of different ways. Okay. And the work done depends on the path you take. Okay. So the work done is the area under the curve. Okay. So the work done is path dependent. All right, let's go back to this example. Okay, when this was expanding, what made it expand? You were adding heat. Okay, so the amount of heat you added turns out to be path dependent as well. Okay. What does the statement mean? So when your system went from this initial state to that final state, the work done was path dependent, and the heat that you added to the system was also dependent on the path. The heat added in this process was different than the heat added in this process, than this process, and so on. Okay. Okay. And it turns out so. I started the chapter by writing the equation wrong. But you guys knew that.
That's why I come in late.
I'll give you that one. The first 5 minutes are the most important of the lecture. That sets up the lecture. Okay, so here's the thing. So the heat added is path dependent. The work done is path dependent. But the difference, which is the change in internal energy, is path independent. Okay? So when you go from this initial state to that final state, well, the internal energy is just a state function, meaning it just depends on the state of the system, where you are located. So the internal energy at this point is whatever value it is, and the internal energy at that point is whatever value it is. And the change in internal energy is just the difference of the energies. It doesn't matter how you got there. Okay? So here's the neat thing about this equation. The heat added to the system is path dependent. The work done by the system is path dependent. But the difference, the change in internal energy, is path independent. Okay? So the change in internal energy of the system is path independent. Okay? Internal energy is a state function. Okay? All right, so there's the first law of thermodynamics. Again, Q is the heat added to the system. W is the work done by the system. Q minus W is the change in internal energy of the system. Okay. Again, the financial analogy is this is your earning, this is your spending. Earnings minus spending is equal to increase of your bank balance. Okay. And like I said again, each one of these terms can be positive or negative. Okay. So Q is positive when system absorbs heat. Q is positive when the system absorbs heat. W is positive when the system does work. Delta E is positive when the internal energy of the system increases. So in physics, we look at it from a systems perspective. Sometimes engineers use a different sign convention, and you might see this equation in your engineering textbooks. Okay. I'm, of course, biased. So. All right, so that's the first law of thermodynamics. Okay. Now all we're going to do the rest of the chapters, we're going to introduce various processes and then tell you something about each of these terms. That's the rest of the chapter. Okay. All right. And the system will work as the working substance in the system will be a gas. It'll be an ideal gas. Okay. So it's useful to keep the ideal gas law in mind. Okay. So we'll keep this in mind. ISO means constant. Okay. So isovolumetric process. So here's a process where the volume is constant. Okay. And remember, so let me show you a process and then we'll come just so. Okay, so here is our. Okay, so let's say this is our initial state. Okay. What I'm going to do is I'm going to isovolumetric process. I'm going to keep the volume constant. So I'm going to heat this gas. And as you can see, the pressure and temperature increases while keeping the volume constant. How are we going to represent that process on the PV diagram? You saw that the volume was constant initial and the pressure increased. Okay, we are not able to tell you what the change in temperature is, but we could use equations, other equations to calculate the change in temperature. But in this diagram, all we are showing you is that process, the pressure went from this initial point to the final point. Here's an isovolumetric process. Okay? So you have to imagine the physical process that happens. Okay, so all these processes, you can imagine what the process is. Okay, isovolumetric process is any vertical line on this PV diagram. Okay, isobaric process, constant pressure process. Okay, so in a process where the pressure is held constant, and we can do that here. We'll keep pressure constant, and if I'm holding the pressure constant and I add heat to the system, what will happen? The volume will go up. Okay, and you see that's what's represented here. I add heat, and the volume increased. Okay. Isothermal process, this is an important process. In an isothermal process, you're going to keep the temperature constant. Okay? And so you guys have seen that this is the equation of a hyperbola. Okay? So P equal to nRT over V. So this is your Y, this is your X. There's the constant. You're holding temperature constant. Okay? So when you hold temperature constant and you increase the volume, the pressure decreases along the hyperbola. Okay? So let's see this process. So we're going to hold the temperature constant, and I'm going to decrease the volume and watch for the pressure. The pressure will increase. See the pressure increase. Okay. So what I did was I moved along this curve in that direction. Okay. All right, so here are the three processes. And an adiabatic process, is where you are not adding any heat to the system. Okay, so if the system does work, it has used its internal energy, and so it'll cool down if this gas expands. So in an adiabatic process, no heat is exchanged. Okay? And in an adiabatic process, an ideal gas goes along this curve. Okay, you see when the gas is expanding, it's doing work. How much work is it doing? It did this much work. Where did the energy come from? It used its bank balance. So when it used its bank balance, what will happen?
It goes to zero, but it doesn't refill.
Its temperature decreased. Each of those air molecules slowed down. That's how they spend their energy. And you see, you went from a higher temperature to a lower temperature. Okay? So that's what happened in an adiabatic process. Okay? All right, so looking at this equation, if you did work and this was zero, if you did positive work, your internal energy decreased by that amount. Okay? All right. A cyclic process, this is an important process because the gas in your car is taken through a cycle. You know? So in a lot of engines, you use cyclic processes. You'll learn about Stirling engines. So in a cyclic process, you come back to the original point, so delta E is zero. Change in internal energy is zero. Okay? So whatever amount of heat so delta E is Q minus W. Whatever amount of heat you absorb, that's how much work you did in that cycle. Okay? And it turns out that if you go clockwise, then the work done is that. If you go counterclockwise, then you've done negative work. Okay, so this is positive work, and this would be negative work. Okay. This is positive work because this curve is at a higher location, and that area is greater than this area. Okay. All right. In an isothermal process, the temperature is constant. The temperature is constant, meaning the average kinetic energy per particle is constant, and the number of particles are constant, so the internal energy doesn't change. Okay, so in an isothermal process, the change in internal energy is zero, and so the work done is equal to the heat absorbed. And again, always keep this in mind. All we are saying is stuff about these terms. In an adiabatic process, Q is zero. Okay. And if you do any work, then your internal energy decreases. If you do positive work, if you do the 100 joules of work, then your internal energy decreased by 100 joules. Okay, so now we'll look at an isothermal expansion. What is an isothermal expansion? Constant temperature, isothermal. Okay, so you're moving along a hyperbola on the PV diagram. Okay, so when you expand, the work done by the expanding gas is this area. And here, in this case, it happens to be a simple integral. So the pressure as a function of pressure is nRT over V. So that's the pressure as a function of volume, and we're going to substitute that there and do the integral. Remember, this is an isothermal process. This is constant, so this is a constant. We'll pull it out. And then integral of dV over V is just log V. Okay. And then you apply the limits, so you get this. So the work done is nRT log V final minus V final over V initial. All right, so this expression has all the, you just want to make sure that it has all the right behavior. So for example, if the gas did not expand, how much work did it do?
Zero.
0. So if V final is equal to V initial, that is 1, and log of 1 is 0. Yeah. If the gas compressed, for instance, if you went in that direction, how much work did the gas do? Did it do positive or negative work? Negative. So if V final, look, Alicia answered the question. Thank you. If V final is less than V initial, that's less than 1. Log of a number less than 1 is negative. Yeah. All right, so this has all the right behavior. Yeah.
When does it do negative work? When it shrinks?
Yeah, so our convention is when the gas does work, when it expands, then it does positive work. So when you do work on the gas, the system has done negative work. So when you're using a bicycle pump, you're doing work on the gas. So we say the gas did negative work. That's the convention. In engineering textbooks, when you do work, they take that as positive work. So, okay. It's just a matter of convention. Okay. What is an isobaric process? Constant pressure. Okay, so it's those horizontal lines. And the work done is just the area under the curve, and the work done is just pressure times change in volume. And again, if the final volume is greater than initial volume, then the gas did positive work. If the final volume is less than the initial volume, the gas did negative work. Okay, so this was positive work, this was negative work. Isovolumetric process are those vertical lines, and 0 work is done. So you guys remember when we were talking about solids and liquids, we only defined one specific heat. In solids and liquids were to measure the quantity of solids and liquids, what's easiest to do? Mass. And then we had one specific heat. But when it comes to gases, what is the easiest way to measure how much gas you have? Not volume. Moles. Number of moles. Okay? And you saw that, let's say I heat this table. Okay? Does this table, will it expand?
Yes.
It'll expand, maybe 1 part in a million. Okay? So when it expands, it does do work, but that's negligible. Okay? So we never worry about that. But you heat a gas, and a gas can expand 300%. It can do a lot of work. Okay? So you have to account for that. Okay? So that's why we have to define 2 specific heats. When you're heating a gas, what is it that you have to do? You have to speed up every molecule. Okay? So you are spending energy on that. And if the gas is expanding and doing work, then you have to spend money on that as well. Okay? So heating a gas when it's not expanding is easier to do than heating a gas when it's expanding. Right? Everybody understand that? Okay, so that's why we have 2 specific heats. QV, you're adding heat at constant volume. Okay? So this is the molar specific heat at constant volume for a gas. Okay? And this is the molar specific heat at constant pressure. Okay, so we define those 2 extreme limits. Of course, you can heat a gas while you're changing its volume and changing its pressure and all that kind of stuff. So you can't define a specific heat for that. So we can only define specific heat for these 2 extreme limits. Okay. Again, which one is bigger? You think about it, you can answer that question. Which one is bigger, this one or this one? CP. Why?
I can't remember. I just know it is.
Because you need no. You need,
Go ahead.
it's to do with how it's harder to heat a gas as it's expanding, so the constant pressure.
Harder is not the right word. Okay, so when it's constant volume, all you're doing is, when you're heating, all you're doing is speeding up the molecules. When it's constant pressure, it's expanding. You're heating up the molecules, and in addition, the gas had to do work because it was expanding. So you had to spend extra money doing work. Okay? Yeah, so, you guys understand that? Cp is always greater than Ce. Yeah? And what we'll see is, for an ideal gas, Cp minus Cv is equal to R. Yeah? So for an ideal gas, it doesn't matter what the gas is, methane, hydrogen, nitrogen, oxygen, or whatnot. Yeah? Okay, so this is the molar specific heat at constant volume. This is the molar specific heat at constant pressure. Okay. We've already derived this expression before, the expression for this before. So let's say we saw that the internal energy, help me out, I forget this. How do we calculate the internal energy of a system? Each particle has F degrees of freedom. What does F degrees of freedom mean? Okay, so let me back off. How many degrees of freedom do those last column of atoms have?
1. No, sorry,
3.
3. Sorry.
Yes.
Yeah. 3.
How many degrees of freedom does the nitrogen molecule in this room have? This nitrogen molecule is diatomic. Let's see if Alicia can answer this.
Bro, what?
Not, my name is not bro. Yep.
Is it 5?
5, very good. What are the degrees? 1, 2, 3, and rotational degrees of freedom. Okay? And if we were on the surface of the sun, how many degrees of freedom would these diatomic molecules have? 7. You'd have the rotational and the vibrational degrees of freedom. Okay? All right. So to calculate, so you see, as the degrees of freedom change with the temperature of the gas. Okay. Yep.
This is kind of off topic, but why does vibration count as 2 degrees of freedom?
This guy is vibrating, and this guy is vibrating. Yeah. Mm-hmm. They can independently vibrate. So, okay. These modes, there you would think that these modes are higher energies, and so only. Okay. So now that you ask, so why are rotational? There's only 2 rotational degrees of freedom. 1, 2. How about this guy? That takes too much energy. You'd have to heat the gas to 500,000 degrees before that vibration comes up. That's like me trying to buy a Lamborghini. Yeah. I'm going to be friends with Winnie because she can buy me a Lamborghini. All right, so we understand the degrees of freedom. What I want you to remember is the number of degrees of freedom for the same particle can be different depending on the temperature you're at. Okay? All right, so how do you calculate the internal energy of the system? How much energy does each degree of freedom contribute? 1/2 kT, that's the equipartition of energy. F is the number of degrees of freedom. So each particle is contributing this much energy to the system, and then just multiply it by the number of particles in the system. Okay? So I'm just going to do the easy derivation. There's a couple of complicated derivations that I'm going to skip. Yep. CV is defined as 1/n del internal energy divided by del T. Okay, so let's do this. And derivative of this, that kills that. So, oops. This is the number of moles and this is the number of particles. N times K, the Boltzmann's constant, is the number of moles times R. So CV is F by 2R. Okay. So where does that expression come? QV equal to NCV delta T. Okay, so for those guys on the end, what is CV for them?
Uh,
3/2 R. So what that number tells you is if you take 1 mole of those gas, R is about 8, 3/2 of that is 12. Okay, so if you take 1 mole of any of those gas, heated by 1 degree Kelvin, what you need is 12 joules of heat. So that's what that tells you. Pretty neat. So just like that, now you know something about that guy. Okay? And what you'll know is, see, there's 6 different gases, all different weights and stuff like that. But you take 1 mole of that, and it takes the same amount of heat to warm it up by 1 degree Kelvin. So the heavier the molecule, yep, the heavier the molecule, the less it's sped up, but its kinetic energy increased by the same amount. All right. All right. So there's the expression, and this derivation is showing for a monoatomic gas which has a degree of freedom of 3. But we have derived the general case, F2 over R. Okay. So for monoatomic gases, it's 12 joules, 12.5 joules per mole per Kelvin. What it's saying is, if you take 1 mole of the gas, you need 12.5 joules of heat to warm it by 1 degree Kelvin. Okay, that's what that's saying. Okay, I'm not going to go through this derivation. This is showing you Cp minus Cv is R. Okay, this derivation is for an ideal gas. Yeah. Okay, and if you want, you can either look at it or come by my office. But anyway, so I'll very quickly go through this. Q is internal energy times W internal energy. So if you add an infinitesimal amount of heat, this is a infinitesimal change in the internal energy, and that's the infinitesimal work done. This is equal to NCP delta T. So we are doing this process at constant pressure. Change in internal energy is related to the CV. It can be given by NCV delta T. The amount of work done is that. Okay. And PV equal to. Okay. So if you do a process at constant pressure, okay, if the volume is changing, how did the volume change? The pressure is constant. If you want to increase the volume, you have to increase the temperature. Okay, so P delta V is NR delta T. And that's what that is. Okay, see, and the reason we wrote it is, see, now delta T cancels. Okay, N cancels, and you're left with Cp minus Cv equal to R. What's neat about this derivation? Did I tell you what the gas was? No. What was the basis for this derivation, this equation? So as long as a gas behaves ideally, I don't care what gas it is. Yes, Cp minus Cv is R. Okay. Now here's something that we define that you'll use all the time. Gamma, which is the ratio of specific heats. Okay. And look at this table. Here's gamma, the ratio of specific heats, and for various gases. So here's what gamma tells you. What are these gases? The noble gases, monoatomic gases, and look at that, gamma is 1.67. What are these gases? Diatomic gases, and gamma is 1.4. Here are more complex gases, and gamma is less than that. Okay, so gamma tells you how complex the molecules are, the particles of the system are. Okay. And gamma is the ratio of specific heats. Okay, by the way, so as long as these guys are behaving ideally, so these are experimentally found values. Cp minus Cv is R for almost all of them. Okay. So here's a methane molecule, and it has multiple rotational degrees of freedom. Okay. So you saw that Cv is F by 2R, and Cp is F by 2R plus R equal to and so gamma is Cp over Cv, which is F plus 2 over F. Okay. And you see, for an infinitely complex gas molecule, F would be infinity, and this ratio will tend towards 1. So the more complex a gas is, gamma tends towards 1. Okay. The least complex you can have is a monoatomic gas, which is 3. 5/3 is 1.67. Okay, so gamma goes from 1.67. It'll tend towards 1 the more complex the gas is. Okay. Cv is F by 2R. We've seen this graph before. Okay, and this is for hydrogen. Okay, so Cv is 3/2 R for a hydrogen molecule. Hydrogen is a diatomic molecule. Okay, so if you have a hydrogen gas under 100 degree Kelvin, those rotational degrees of freedom are not in play. What does that say? What do you mean by the rotational degrees of freedom are not in play? At those low temperatures, there's not enough energy to excite these rotational modes. Okay. If you take the hydrogen gas to that temperature, now the degrees of freedom are 5/2. So now you have enough thermal energy to excite these two modes of degrees of freedom. The vibrational degrees are not in play. You have to go to the surface of the sun where the vibrational degrees of freedom are in play now. You can excite them. Okay, so the same gas, it's taking about 12 joules to heat 1 mole by 1 degrees. Here it's taking 2.5, 20 joules to heat 1 mole by 1 degrees. Here it's taking, on the surface of the sun, it's taking 3.5, 28 joules to heat 1 mole of hydrogen gas. 12, 20, 28. Okay, you guys see that? The same gas is behaving differently. All right, I'm going to state a couple of things, not derive them, but I'll. Okay, so let me motivate this. Okay, so here's a system that's oscillating. The motion is fairly complicated. Is there anything that is constant during this motion?
The total energy.
No total energy. Okay? So we've been doing this all along. We like to say if you have some kind of motion, is there anything that is constant? Okay, so that's characterizing the system. Here's another important one that we are all thankful for. Okay, as the Earth goes around the sun, it has kinetic energy plus potential energy, gravitational potential energy, and that's mechanical energy. The mechanical energy of the Earth has been constant for 5 billion years. So its orbit hasn't changed, and we're happy about that, right? When is this true? When is mechanical energy constant? There's no friction. Friction converts mechanical energy to heat. Winnie, go Winnie. All right. So in this motion, we're able to say something. Mechanical energy is constant. You also learned that the angular momentum is constant for this motion and other things. Okay. So for dynamical systems, we want to be able to say things that are constant. Okay. Here's an adiabatic process. When you take a gas and let's say it expands, what is an adiabatic process?
Heat's exchange with
No,
surroundings.
no heat is exchanged. Okay, so heat doesn't flow into the system or out of the system. So let's say you make gas expand in an adiabatic process. This is, if you're using a cycle pump, you draw air in. Okay, so we want to talk about a fixed particle system, but here's an adiabatic process. So we want to be able to say, what we find is, in this adiabatic process, this fellow is constant. You take the pressure and volume at this point, raise it to the power of gamma. You take the pressure and volume at this point, raise it to the power of gamma. You find that value is constant. So everywhere on that adiabatic curve, it turns out that's constant, as long as the gas is behaving ideally. Okay, so that's the statement. Now, of course, so this goes through the proof. If you come by my office, I can show you how to prove it. And then you can use this equation and PV equal to nRT. This plus this, using those two equations, you can show that along that curve, TV to the power of gamma minus 1 is also constant. Okay? And you can see that as you're going through on that adiabatic curve, the temperature is also changing. Okay? So temperature and volume to the power of gamma minus 1 is constant. Okay? So here are two statements we made about the thermodynamic variables. Okay? All right. So here's a slab of air. Does this weigh anything?
Yes.
Why isn't it falling down?
There's air beneath it.
What's that?
There's air beneath it.
Well, there's air above it too.
It's moving at 500 meters per second.
I'm sorry?
It's moving at. The air below it is more dense, probably, or it's just on its way down.
Okay. So this not falling down, it has weight. Its weight needs to be balanced. Okay, so that tells you there must be an upward force. How do you bring the upward force? The pressure at the bottom has to be higher than the pressure at the top. So let's go back to our ideal gas because we are experts at that. You want the pressure, so we're going to assume that the temperature is the same everywhere. This is the same. If the pressure at the bottom needs to be higher, then the number of moles of gas per unit volume needs to be higher. The density of air needs to be higher.
Oh, cool.
Yeah, very cool. Yep. Okay. So just $300 of physics and a little logic gets you far. All right. So we're going to derive the model, the density of the atmosphere, assuming a constant temperature. The temperature in reality is not constant. It decreases by about 2 degrees every 1,000 feet, something like that. Yeah. All right, but we're going to throw reality out the window. We'll consider the ideal case, okay? So again, I'm not going to do the derivation. Okay, so the change in pressure, okay, is equal to kBT times, okay, so all changes in pressure is coming from the change in the molar, is the molar density, okay? Number of moles per unit volume. Okay, so if you go through the derivation, it turns out that the molar density, number of moles per unit volume, decreases exponentially. Y is the height above ground, and M is the mass of the air molecule, G is acceleration due to gravity. N0 is the density at ground level. So the atmospheric density decreases exponentially. Okay, back in the day, this is about 25 years old story, or maybe 15 years old. Some guy was offering a $10 million for a private company to reach space. And space was defined as 100 kilometers. So you had a price, $10 million price was offered for a private company to launch the rocket to 100 kilometers. But, so that's how they define that. But the density decreases exponentially, and if you go 5 miles up, you've crossed half the atmosphere. This much atmosphere weighs as much as the rest of the atmosphere. Okay. At about 8.1 kilometers, density is about 30 n naught times 1 over E, and which is about 35%. In Denver, the density of air is about 80% that of at Daytona Beach. Okay. 8.1 kilometers. Mount Everest is 9 kilometers. So the density of air is about 30% the density at Daytona Beach. That means the amount of oxygen is 30%. Mm-hmm. All right, so here is the important expression. Okay, so you can see that. Okay, so you can think of this as sort of a probability. See, what is that? That's the potential energy of the air molecule at height y, gravitational potential energy, and that's kT. Okay, so from there, you can see, you can think the probability of a particle occupying an energy level E can be given by n naught, which is a constant, e to the power of minus EKT. The exponential law of molecular distribution can be generalized. Thus, the number of energy density of molecules having the number density of molecules having energy E is given by that. This equation is known as the Boltzmann's distribution law. The probability of finding a molecule in a particular energy state varies exponentially as the negative divided by kT. Okay, so this is important. So what this says is, do you guys know how lasers work? What? No, no. No, what I want to know is, what's the deal about lasers? See, the big deal about what's the big deal about this beam? It's so the beam width didn't change. I take a flashlight and the energy spreads up. So how does this happen?
A lens?
Huh?
Is there a lens?
No, it's not a lens. All right, so what? Is she making fun of you?
Yeah.
But you don't care, right?
Yeah.
Exactly. All right. So for lasers, here's how they work. Okay. So let's say a system has various energy levels. Now, what this is saying is, the higher the energy level, the probability of occupation is lower. Right? Bigger this number, smaller this number is. Okay. So this is the probability of this energy being occupied. So you have a system who has with all these various energy levels. So if you have 20 particles, most of them will be in the ground state, then a few are excited. What will happen if you heat this system? More get excited. There'll be more and more there. But the number at the top will always be less than here, which will be less than here and there. Okay? The greatest numbers will always be like that. All right, now let's simplify the problem. Let's do only 2 energy levels. Okay? So no matter what temperature you are at, the number at the top will be less than the number at the bottom. When do you think they will be equal? I'll write down the expression for your benefit. When they're equal, then that means the probability of this level being occupied is equal to the probability of this level being. When the temperature is infinity, any finite number, okay, gives you the same value. So this is infinite temperature. Here's something mind-blowing. What the heck is this? What is that? This is really crazy. How could you have this? So this is the higher energy level, you have more occupation, higher probability of being occupied. So if the temperature were negative, then this could be possible. So this is, you can think of this as negative temperature. This is called population inversion. That needs to happen in lasers. Okay, so if you take a normal atom excited, it'll fall back within a billionth of a second, trillionth of a second. Okay? So in a laser system, you take an atom excited and then you have a metastable state where it decays there, and then it takes a long time to fall back here. So in a laser, you need systems like that, and then you populate these guys more than the down state. And if in a cavity, you have a photon going like this photon will make him de-excite in coherence. So they will all be in lockstep, and that's how you have this thing. Okay? So lasers are pretty amazing things.